Yeah, so my name is Hans Josephsen, and I'm actually coming all the way from Norway for this. Not just this, but for our company meetup. So it's fun to visit Warsaw. In this talk, I'm going to be doing a little bit of live coding as we get into it. So let's hope everything goes as intended. I'm really banking on that one. So let's all hope together for that. Yep. So my talk title is Object Detection in Elixir with Axon. And I think hopefully all of you know what Elixir is, but there's two words here that I want to explain to begin with. That is object detection and it's Axon. So let's start with object detection briefly. So object detection is a problem in machine learning where you get an image as an input and you try to detect like any of a given number of classes in that image, right? So you get the image as an input, you output bounding boxes, and you get probabilities of that bounding box being a car or like a person or a cup or something like that, a chair. So this is like an example of what the output of an object detection model might be. You get an image and you like annotate it with like a truck there and a car and whatever. The second piece of the title is Axon, which hopefully some of you have heard of before from the various talks on it. It's the machine learning framework for Elixir. And the whole sort of idea behind it is that you build up your neural network using these layers. So you give it like a tensor, which is like a multidimensional array as an input, and you pass it through the different layers until you get the output, right? That's the prediction from the neural network. Within those layers, you run like NX, numeric Elixir definitions. So the reason why this can run fast is because you can actually take this whole like graph and you can compile it down to something that runs really well on like a GPU or like an accelerator, or as we're going to do today, I'm going to just be running it on like the CPU on my machine, but it's reasonably fast because the model is going to be pretty small and it's going to be, yeah. Okay, so that's like the two parts of the title, but like, what are we actually going to run? So YOLO. That is not something I'm just saying. That's the name of the model we're going to be using. And it's probably like backronymed from that. They wanted to name it YOLO, so they just like found out you only look once. But it actually means something interesting technically as well. So I'm going to be mentioning like the history a little bit. So for object detection, before YOLO existed, there was a different architecture where you had like two different networks. You had one network called the region proposal network, and the job of the region proposal network was to identify different bounding boxes, right? It didn't care what was in it, just like, okay, this is an object here, probably something interesting. And then there's a second network called the classification network, which then takes in every bounding box and then tries to classify, like, is this a car, is it whatever, like a chair, whatever. So as you can imagine, this is a bit expensive to run because you have to run first the region proposal network, and then you need to run like a separate classification network for every single bounding box in the image. So what YOLO does different is you take the image and you try to predict the bounding boxes and the classes and everything within like one invocation. And the big advantage here is that you can train the whole network end to end, right? You give it an image as an input, you try to train it on the bounding boxes and the probabilities directly. I'm not going to go very much into this, but like this is how like the general outline of the model looks like. There's a backbone, and the job of the backbone is you take the image in, and then you do like these convolutional layers. You try to like extract features from the image. So say at the image, it's the raw pixel values, but as you go like up in the backbone, things start getting more abstract. So you might look at like edges or then like higher corners of objects or like circles. So as you go upwards there, then might start to represent more like abstract things in the image. And then you have the neck, which then you can see it goes inwards and then it sort of goes down and up again. So this takes the features and it tries to like integrate them and match them together and like generate like more like semantically meaningful like values as you go down in the network. And then lastly, you have the detection head, which then takes these from the neck, call them feature vectors, and it tries to predict like, is this an object, probabilities for the different objects, and it tries to predict a bounding box, like how big is it specifically. And there are many YOLO models. We're up to version 8, which is what we're going to be using today. There's many different ones. But we're going to be using an implementation of YOLO v8 by a company called Ultralytics because it's really quite nice to use. What's interesting here is that this Ultralytics YOLO v8, it's implemented in Python using PyTorch, which doesn't sound very relevant for this talk here, but we'll get to that in a little bit. Just bear with me. So you can see it like this is just like a graph from the display. You see there's an N there, S, M, L, and X. So those are like different sizes of the same model. So we have the N, which is it's really tiny. It can run on mobile phones pretty nicely and stuff in pretty much real time. But it's not very good. You see like the Coco map. That's like the accuracy of predicting like objects in an image. It's pretty low. But then as you go up in the size, it then goes up in the accuracy, but there's some diminishing returns there. So we're going to be running our model on the CPU. So we're going to be using a small one, and it's good enough for this. But it's really easy to use the other ones, just scaling up. But yeah, I mentioned this is written in Python using PyTorch, not very Elixir-y. How do we do this? How do we get this model that's written in Python over in Elixir? So the answer to this is something called ONNX, Open Neural Network Exchange. So this is like a project with a runtime, but what we're interested in is the file format. So it's like protobuf-based file format that stores both the architecture of the neural network, like, okay, here's the input image, then it goes through like a convolution layer or different layers, and then the entire structure with the weights of the model is represented in that format. So this is like an image from the ONNX project. And you can see there, we can take models from loads of different frameworks, like PyTorch is a popular one, TensorFlow, a lot of these for machine learning. You can then export it into any other ones and run it. And there's actually a project called Axon ONNX, which, you guessed it, you can import and export Axon models to and from ONNX. So let's actually like put the little Axon on there. We should get that in the actual image as well. Okay, so just to summarize a little bit what we're going to be doing, we're going to be exporting our YOLO v8n model to ONNX. We're going to be importing it in Elixir using Axon ONNX. We're going to run that on an image, and we're going to try to visualize the results, like look at how that works. So this is where the live coding part starts. So let's see how this goes. We're starting in the terminal here. I mentioned that we're going to be using the YOLO implementation by a firm called Ultralytics. So we're going to install that using pip. So install. And then I already have it installed. I don't want to mess anything up here. I'm going to do a dry run. I don't trust the conference Wi-Fi. I'm sure you can understand. So there's a pip upgrade available apparently, but we're not going to deal with that. But you can see already satisfied. So we have like the Ultralytics package installed in pip.
Can you raise the font a little bit?
Command plus. This is going to mess up. Yeah, this is going to mess up. Hold on. We're not going to be doing a lot in the terminal, so it's probably fine. Okay, that's good. Okay. So we have it installed. We should have a pip or a YOLO command, which we can run. And it'll just give us, I mean, hopefully, yeah, it'll give us some help here. But specifically what we're going to do, we're interested in the export command, and we're going to export the model to ONNX. So like, it's just a CLI to interact with the YOLO model they implemented, and we want to export it to ONNX. So, YOLO, export, and then we want our model, YOLO v8n. So that's like the n, like the lowest, the smallest model version. And we're going to export to the format, ONNX, and then we're going to specify an image size. And in this case, we're just going to do 640 by 640. It's pretty standard image size. Or IMG set. 640. And then when we run this, it's going to do something, and it seems to have worked. You can see we have our, saved as YOLO v8n.onx. So we're going to get the path. And we're going to, you notice there that it's suggesting that we visualize our model using something called Netron. And Netron is like, it's a browser application that you can just open in a browser, and you can upload your ONNX, or it supports many other files as well. And you can see like the structure of it. So we're just going to give that a try. I'm going to switch to the browser here. So I have Netron open. It's just like netron.app webpage. And I'm going to select our model. And just for curiosity, here we can see how it actually looks, and it's pretty big, but you can see specifically like the different operations here. So there's like a mul, which is like, that's a multiplication operation, and there's a convolution operation, which is like you take some weights and you slide it over the image, and a sigmoid split. Many different operations. It's pretty big, but we can see all of them, and we can look at the weights too if we wanted to, but we're not going to spend too much time here. But it's a pretty nice and cool tool. But how do we actually get this into Elixir and run? So we're going to use Livebook for our session here today. So I'm going to just create a new notebook, and let's name it there. And then we need our setup, right? We need to install some packages, and I'm going to put in some utilities as well. So for this, I'm going to cheat a little bit. I'm going to paste it in, but we're just basically installing a bunch of packages, and there are quite a few functions there, like 3 of them, but these are just utility functions for like drawing some rectangles on an image and like drawing some text on an image. So there's not a lot going on here, but I don't want to do that on stage here today because it's a bit fiddly, but that's there. And then I also have just like a list of the classes that the model supports. And I've pre-imported that, but it's documented on like the web page for the model, so that should be pretty easy to get. Okay, so we're going to run that and hope everything finishes quickly and correctly. And yeah, evaluate it, so things should be good. So the first thing we want to do, we want to actually load our model. So we're going to start with our path. So this is just what we just exported using the YOLO CLI. And we're going to use, I mentioned Axon ONNX. So we're going to try using Axon ONNX.import. And we're going to import our path. And then if this succeeds, you should see the first thing it returns is the Axon, just like an Axon data type here. And that's a representation of the whole neural network, all the nodes. But that's just the structure. So it's going to return a map. And this is going to be a map of all the different, like the node names, and then the different number parameters, right? Because this is a pre-trained model, so we're going to use those parameters to actually like do inference or something. So we're going to pull these 2 values out. We're going to have the model, and we're going to have the params. And then I mentioned Axon is a thing in itself, but then we also want to use, we want to compile this to native code to make it run quickly. So we're going to use Axon.build and pass it our model. And then we're going to give it the backend of EXLA. So all this does is it takes the model, it compiles it to something that runs fast on the CPU. So we get 2 functions there. The first function is a initialization function. So if we're training a neural network, right, we need a way to get these parameters initially, right? We're going to initialize them with something random probably. And what this prediction function or this init function is going to do is it's going to give us just like an empty randomly initialized parameter map. But we're not going to be doing this today because we have a pre-trained model. Sorry?
Compiler, XLA. The option compiler, EXLA.
I think this works. I'm gonna try if this works. Should it fail if?
Yeah, we're not checking the options apparently. Okay,
well, I'm gonna trust you. I'm gonna hold you on this. Okay. So I'm just going to print out the model because it's going to be interesting for reference, but we have our inputs, which is the image. You see these numbers here, which I'm going to talk a little bit about. It's 13640 by 640. This is suspiciously similar to the image size we specified in the export, and that's no coincidence because this is like the shape of the input tensor. So the topmost, the one in the beginning, that's the number of batches, and I'm going to explain that a little bit. But the second one is 3, so that's like the colors R, G, and B. And then 640 by 640 is the pixels. So you can think of this as like nested arrays. You have a topmost array with only one element. Below that you have an array with 3 different like image planes, red, green, and blue. And then you have 640 by 640 pixels within that again. So, and batches, that is, when you're running stuff on a neural network accelerator, it's really good at like churning through loads of operations quickly. But often you want to work on a large amount, you need to give it enough data to sort of ramp up to speed. So the batch here is, you maybe give it like 100 images at the same time, and it just loads those into memory of the accelerator and then does the inference and everything. But since we're doing on CPU and we're just testing, we're going to do one today. Okay, so we have our model, we have our predict FN, which is what we call to do the prediction, and we have our params, which is specifically what weights the network is initialized with. But what we'll need also is we'll need an image to actually do the prediction on. So this is where we're going to be using Kino to read in an image and work with it. So we're going to be Kino.input.image. And then when we run this, we actually get this like nice image selector inline in our Livebook. So we're going to be using this to take a photo. So everyone better smile. I'm going to be.
There's dark light.
Oh, using light, yeah. There we go. Let's hope it finds something there. So now we have taken our image, and then we need to actually read it into our Livebook and get it into a format that the neural network can work with. So we're going to start by reading our image input, and it's going to return a data structure with a data key, which is just like a long binary containing the image data. It's going to contain a format, which is RGB, pretty nice, that's what we want. And it's going to contain a dimension, so height and width. So now we need to convert this into like a tensor in the format that our neural network expects. So what we have, let's just write it down. We have the binary. It's height times width times 3. It's in the format U8, right? Because every pixel is represented as an unsigned 8-bit integer. Each of these values in the binary. And it's in the range 0 to 255. And what the neural network needs, and this is also documented in the documentation for the model, it needs a tensor, obviously, because that's what Axon works with, of shape 1 for the batch, 3 for the 3 color planes, and then 640 by 640. And it's going to be expecting a float, 30-bit float, in the range 0 to 1, right? So we need to scale it, we need to reshape it to fit that. And for this, we're going to be using NX. So we're going to start with the data, and we're going to do NX.from binary, and we give it a type to convert from, which is an unsigned integer, which is what the pixel represented as. So we're going to get a tensor here. It's going to be in the format U8, right? That's what we told it about. And it's going to be 921,600 elements long. Like, that's the same length as the binary. And we need to actually reshape that into, so the shape the data was of is 460 by 640. So we're going to do NX.reshape. So what reshape does is it just takes a a tensor with data, and it just reinterprets the dimensions. So here we have a flat tensor that's really, really long, and we want to just, the data below is the same, but we just want to start interpreting it as arrays of image data, right? So like nested arrays instead of just a flat array. So oh, it's not that doesn't take access. That just takes a tuple. So now you can see we went from what was below here is a really, really long tensor, and we now reshaped it into, it's containing the exact same data, because if you look at the data here, it's 255, 241, 211, 255, blah, blah, blah. But afterwards, it's just like now in a nested array instead, right? So it's still living in the same order, but we just like made a new shape for it. What we have right now is 480 by 640. So you need to get it into 640 by 640, which is what the network actually expects. So for this, we're going to use nx image dot center crop, and this is gonna if the image is too large, it's gonna crop to the center. But if it's too small, it's gonna like pad it with black bars. So we want it into 640 by 640. You can see our tensor is still a U8, but it's now 640 by 640, and then our 3 RGB pixels in each side. So the next problem we have is our pixel data, RGB data, is in the innermost dimension here, right? It's in the innermost part of the tensor. But what the neural network expects, it expects it's on the top, right? It expects 3 image planes, while in our current format, the pixel data is in the innermost part. So we're going to use a really powerful operation in NX called transpose. And you might recognize this if you've done any like linear algebra or anything in university, that transposing a vector or a matrix is like flipping around the axes. But this is like a general transpose. We can actually specify the new order for every axis. So we're going to specify the axis. So we want the first element in the tensor, like the first dimension, to be the uppermost one. We want the last one to be, hold on. Oh, we want the last one, which is the RGB values, to be the topmost one. And then we want like the 0th and first, which is like the image dimensions, right? So this one should go to the top. 640 by 640, those should go below the image planes. So if we run this, then you can see that flipped. Now it's 3 times 640 by 640. And then this is like the home stretch for this transformation. We need to convert it into a float, 32-bit float, and we need to convert it into the range of 0 to 1 instead of 0 to 255. So we're using nx.as type f32. And now we have the muscle float, but they're still in the range of 0 to 255. So we need to do nx.divide 255. And that's going to divide every element in the tensor by the scalar 255. So this is the format we want. This is good. So we're going to assign that to a image tensor variable. And then the last part is there's like an empty like batch dimension here, which we just want to add to the top. So we do make a new batch variable and nx.new axis image input 0. So wrong variable. So all this does is it just adds a new empty axis with a size 1 on top, right? So before it was 3 by 640 by 640, now it's 1 by 3 by 640 by 640. Exact same data underneath, nothing different. Now we need a way to actually display our image, because this is just a tensor. We need to look at how it looks like. We're interested in, like, we've transformed the image now. How does it look like at this point? So we need a way to render the image back out. So we're going to be using, later on for drawing images, we're going to be using a library called image. So we're going to be using the same one to actually show the image in Livebook right now. So we take our image tensor, which we just made, and it's of shape like 3 by 640 by 640. We do transpose again. We need to do transpose because, again, the image library expects the pixel to be innermost. It's a bit awkward, but we just need to do this to display the image. And then we multiply it by 255 because it expects a normal like 0 to 255. And then we do image.from NX. And this is going to return an OK tuple with our image. So we just need to pattern match to get that out of there. And we print our image. And here we can see that we have our image as before. But with this, at this time, we have like these nice black bars at the top and bottom, right? Because we padded it to get it from 480 or something to 640 in height. This was the NX image, so the center crop operation that did the padding. Then this is a bit awkward, but the image library we're using again, it's a NIF. So when we're making this image, oh wait, I'm printing the wrong. What did I do here? Okay, well, because the image variable here, that's a variable represented in a NIF. So when you do stuff like draw on it, it's gonna actually make mutations to the image, which is not very functional and not very Elixir-y. So we're gonna have to make a new one every time we make changes. We want to draw to it over again. So we're just gonna make an anonymous function here that just makes like a new one for us, like this. I'm gonna fix the indentation. And then we're going to call our make image function just to verify that it works. And same as before. Nice. So now at this point, we have our image tensor. We have our compiled model. So now is the time to actually do the inference. We need to call that prediction function with the inputs, the image, and the parameters to get the output. So let's do, we called it predict function here. The parameters are called params. And then the image is called image tensor. So let's do predict fun. And then the first argument it takes is the params. And then the second one is the image tensor. And I think
it should be batch instead of image tensor, right?
Yep, exactly. Because it expects like the top level dimension to be like a batch of 1, and I instead passed it the image data directly, so just like the 3 by 640 by 640. We need to pass it the batch, which is 1 by 3 by 640 by 640. So that's it. It's done. It's pretty quick actually, even on the CPU. It's not a very big model, but what it returns is it returns the top level 1, which is again the different images in the batch. We only have 1. 84, which is the different predictions, like output predictions, or the different probabilities of the different bounding boxes. And then 8,400, which is like 8,400 candidate predictions. So it produces a lot of outputs, potential like bounding boxes, but only a couple of them might be actual like predictions with a high probability of it being an object, right? Because neural networks, they're not very good at producing like dynamically sized inputs and outputs. So the solution with this network is it's just going to spit out a lot of predictions, and a lot of them are going to be really low probability. So we just need to pick those out at some point. So we're not interested, we only have 1 image in the batch, so we just do the index operation to pull out the top level or the single image we have. And then because the functions later on, we really want to operate on each prediction individually, so we just want to move this one, 8,400, to the top and the 84 to the bottom, right? Because then it's like an array of the different like probabilities. So let's do nx.transpose, and then the axes, and then the second axis to the first, and then the first axis to the second, like that. And now we have 8,400 by 84. So let's assign that to our result variable. And then now is the time to actually look at what we produced. So let's just, for the fun of it, let's take our whole thing and draw it on an image and see what that looks like. So we're going to start with the result. And then util, that's like a module I defined in the setup block with a couple of drawing functions. The specific one we're going to use right now is we're going to do draw b boxes, which is like draw bounding boxes. And then we need to give it the bounding boxes as the first argument there. And then we also need to give it the image. So we call our make image function. And this is failing because what it expects is actually like a list of the probabilities. We're giving it a tensor. So we need to do nx.toList, and that should convert it to a list. And we run it. And this is taking a suspiciously long time, but you'll see now in a second why that is. And it's a very red image. There's a lot of bounding boxes that are completely useless, that's like really low probability that we don't care about. And it's just like, there's no image there at all. Like, so what we want to do is we want to actually like filter out the bounding boxes that are of a very low probability. So I have another utility function for doing this, which is util.filter predictions. And this is just going to filter the predictions to like 0.5, right? So anything that it's 50% sure of, it's going to keep in the list. So we can see a couple of rectangles there. That worked really well. We have some people there, we have some chairs, and we have a computer. But there's still a little bit of a problem here, and that is, if you look carefully, there's multiple bounding boxes for each thing. And that is because there are like multiple detection heads like spread out over the image. So it's going to try to predict each one of those 8,400 outputs. It's going to predict objects in like its region, but those regions overlap by quite a bit. So multiple of them are going to predict the same object. So to solve this, we need to use a technique called non-max prediction. And what that's going to do is going to look at bounding boxes that overlap by a lot, and it's going to filter out any bounding boxes that don't have like the maximum probability. So we're going to just remove every bounding box that has, so we're going to find the top, the bounding box with the top probability, and we're going to just like drop everyone that, every other box that has a lower probability and covers somewhat the same area. So that's what non-max suppression does. And we're going to use NMS for non-max prediction, and let's give it probability 0.5, like is what we did before. And this is going to give us an error, but that's because we're actually going to use a different drawing function. We're just going to draw bbox label because it predicts different object classes, but thus far we only looked at the actual boxes. This one draws the boxes with like a textual label, so we can see what actual object the network predicts it's going to be. And then we use enum.zip to zip those predictions together with what we declared here, which is like the different classes. So I'm going to zip that together with the classes. Oh no. And let's hope. There we go. So we have our laptop, we have a couple of people, and we have a cup and some chairs. This is not predicting every person, but this is a pretty like small model. As I mentioned, we're using the smallest one, we're using the N model. If we had used like the X one, it would probably have found a lot more people. We could also have scaled up the input, and it would have given the model more pixels to look at to predict people. But I think this is a pretty good result for like the inference time. It's like under a second, or under, I think it's under like 100 milliseconds on a CPU. So it's like pretty feasible to run this on like a CPU, even on mobile. Yep. So that's the live coding part, which went pretty well, all things considered. But I want to go back to the slides and do like some high-level takeaways real quick before I'm calling it. Let's see here. Yeah, there. So Axon on NX makes it really easy to import models from other frameworks, right? We have the PyTorch model. We imported it. We managed to run it using a pretty short amount of time. However, a lot of the time with machine learning models, you still need to understand like how the model works in order to run it, right? in our case, the model expected like a very specific format of input. It expected the image to be in a very specific like format with specific like ranges of values. So you need to understand how the model actually works at least a high level to run it properly. The same thing applies with the output, right? It outputted like a lot of garbage initially. We had to like filter it and process it to get like the proper predictions we wanted. So the takeaway here, you still need to understand a little bit of how the model works. And the second takeaway is NX is really useful for manipulating this kind of data, right? When you have a tensor, you have a multidimensional array. Imagine like moving the pixel data from the innermost part of that array to the outermost. You have to write like if you were doing Python or something, writing like a for loop or something. That's not a good way of doing it. There's these like higher level operations which enable you to do that kind of stuff in a single line. And is this case with NX, it's going to do it really, really quickly because it's going to offload it to native code and it's going to run pretty efficiently. So that's it for me, I think. So thanks.
Cool, awesome. Thanks, Hans, for the talk. It was really, really cool seeing all of this in action. So yeah, we have some time for some questions if anybody has some. Raise your hand. I'm gonna come over.
So it found a lot of these bounding boxes. You just took, I don't know, some of them. If you would take like, I'm just guessing it's 10. If you would take like 20, would it be still work with this model or?
Yeah. So what we did here is we didn't take like a set number. What we took the boxes that were over like a set probability. So 0.5, which is like it's 50% sure this is like an object of that type. So we just took all those, and then we did, as I mentioned, like NMS on it, which is like it looks at redundant boxes and just removes all the like useless ones pretty much. So we can like lower that to like 0.2, and it's probably gonna detect a lot more people. Or if we like up it to 0.9 or something, it's gonna detect nothing. 0.8, it's gonna detect like 2 people in one person in a laptop. Like, so there's things you can tweak here to like get results better.
Okay, thank you.
Awesome. Thanks for the question. Anybody else? Go ahead.
So have you tried actually putting it into a live situation and kind of have you tried it out, and what was the result like? Have you been able to predict really good all the boxes and everything in the actual working system?
The answer to that is yes. I have like deployed this in a mobile app, like real time, so you go around and it detects boxes. I've also deployed it in an Elixir app, and it's working pretty well. But if it's gonna work well, it really depends on a couple of things. Like mainly, like a big deal with machine learning models is like your input data. You ideally want your input data to look a lot like what you're doing, like using it for in real life. In our case, this is a pre-trained model, so it's trained on like a pretty large data set that someone had made. So it might not be the same type of camera. It might not be taken like in the same lighting. There might be a lot of differences. And for the best results with machine learning models like this, you ideally want your training set to be really, really close to what you're using it for in real life. And if you do that and you pick the right model for what you're doing, then you can get really good results. But it depends on a lot of things, kind of. It's like a tricky subject. Yeah. And I also want to mention like the YOLO CLI tool that I used in the beginning to export a model. So I used YOLO export, but there's also a YOLO predict or a YOLO train, and you can just give it like a data set, and it will like train that model on your custom data set. So you can like pretty easily actually with like a couple of 100 images get like a model that detects things pretty well, which is pretty cool, I think. Yeah, thanks for the question. I hope that answered it somewhat.
Awesome, thanks. Another one?
Yeah, you have mentioned at the beginning that the YOLO is better because it's doing two things at the same time.
It's not necessarily better, but it's like it can be much more efficient and it can be trained end to end.
My question was, is it like less precise because of that?
Is it less precise? Yes, YOLO is not at like the top of the leaderboards, I believe. I believe there's other models that do things differently that are like the way up top of whatever. So we can look at this actually. There's a website called Papers with Code, which let me just Google it directly. Papers with Code object detection. So this is like a leaderboard of different things. Let's see, you can find like Coco, whatever. So this is like over time, the different models that score the highest on this leaderboard. And you can see like, I don't think at any point YOLO is at the top, but it's like right now it's like NAS FPN, intern image, blah, 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 blah. I have no idea what any of these are, but it's like, these are the top like state-of-the-art models, and YOLO isn't on the top here. So it's like less precise, but it's a good like real-world model, I would say, because it's pretty efficient to run on hardware, if that makes sense.
And that's like sorted by accuracy?
Yes, box AP, which is box average precision, which is, precision is like a term used to score the boxes, yeah, the bounding boxes.
Cool.
A question from the humble Phoenix developer. You're mentioning mobile app and NX models. How do you bundle that Elixir code into a mobile app?
Oh, when I mentioned the mobile app that I deployed it in, what we did in the beginning was we exported our model to ONNX, and there's actually libraries you can use in like a mobile app to run an ONNX model on a mobile phone. So I exported it to ONNX, and instead of going into like Axon, I then took it into like a library and ran it in my Android app. That's what I did there.
Thanks.
Thank you. Anybody else has questions? Yeah. Oh, two. Jakub was first, I think.
So in the past I was doing quite a lot of machine learning and something similar in Python. And my question is, how would you compare or how would you rate the experience of doing machine learning in Axon and Elixir to Python? I'm not sure if you have some Python experience with that subject, but maybe you could share some thoughts.
So I worked with I've tried some stuff out and tried to like make some tweaks to some models in Python, and I've done the same in Elixir. And what I would say is, like, obviously the ecosystem is a lot bigger in Python, so you're gonna have a lot more stuff pre-made for you. But when it comes to actually like installing and like running your models, the experience with EXLA and stuff is really, really smooth compared to Python. So if you want to install like all the dependencies you need for something in Python, then you're probably going to have like problems with, oh, like PyTorch, this version doesn't support this version of Python, and it doesn't support like this version of blah, 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 blah. It's going to be a nightmare. In Elixir, that's been really, really, really smooth for me thus far. You're going to have less things pre-made in Elixir, but if you're sort of building something from the ground up, or you're using something that's already made in Elixir, like with Bumblebee, then it's a really good choice, I think, for this kind of stuff. It's just like a fun little thing. I showed here installing, where was it? Yeah, here. Pip 3.10 install Ultralytics. You might wonder why I typed specifically pip 3.10 instead of just pip. So on my Mac, by default, this version of macOS, I think, has Python 3.11 by default, but PyTorch does not support over Python version 3.10. So I had to install like an older version of Python through like brew and use that for this. So yeah, it can be a bit awkward in Python, and Elixir does better on that, at least from my experience.
Thank you.
Yeah, my question was actually pretty similar about how would you see Elixir in combination with this whole machine learning thing on production. Yeah, so based on what you already said, I would like to ask, do you see Elixir shine over Python ecosystem in other terms, like besides developer experience, compared to Python? What would win you over existing mature ecosystem to use this instead? Are there any Elixir specific capabilities like concurrency, process handling that could make this, very fitting for Elixir?
So I think like if you wanted to run your machine learning model in some other like runtime, say like we've talked about ONNX a lot, and ONNX actually has like a library called ONNX runtime, which can run your models as well. You in a lot of times it's pretty easy to like separate the thing that runs your machine learning model into this like separate like server or service that runs, and often you probably want to do that as well, have like a separate service that just does inference, because usually if you're doing like production inference with a model, you probably have some like accelerator, like a TPU or like a GPU on it, and you don't want to like waste that on like you don't want to run like your whole thing on that box because it's like specialized for that thing, and you don't want to waste the resources because running a machine with a GPU is really expensive. It's expensive in AWS, so you probably want to use it for just that.
Like distribution generally and clustering, so that you can deploy those GPUs specific pieces separately on separate hardware. Right?
That is an option, but I mean I don't know how big of an advantage there is over just like running like an ONNX runtime server and just like calling into that, like a really minimal thing, and then calling into it. I'm not sure, but maybe Jose has some opinions on this as well. But I have not deployed anything to production for real, so this is all like just my experimentation pretty much. But yeah.
Okay, thank you.
Awesome, thanks. Anybody else has a question? No? I have one actually, but it might not be related very much with machine learning because there was already a lot of questions. Well, you had there was a moment in the Livebook where you actually asked for like an image input, right? Mm-hmm. I was wondering like how does it know what does the Kino input image function return so that Livebook knows that it needs to render this box? It returns magic. Okay.
Returns the Kino.input, which subscription manager.
Oh, I get it.
Lots of that. Probably like referring to some like stuff in the process that runs the Livebook, blah blah blah. I don't know. You ask Jose.
Jose,
magic.
Could you shine some light on that maybe?
Yeah. So the way Livebook works, the architecture is that we have the Livebook. We have the Livebook operating system process. It's a web application, and every time you start a notebook, the notebook is running on a separate Elixir instance, and they communicate over Erlang distribution. So when you say, look, the process like this, when you say, I want to render, I want to receive an image, I have an image input, then you send that to Livebook. Livebook is going to render it, and it has a reference saying, by the way, if somebody uploads an image, I'm going to send it to this process that is running on this other machine, not on the same machine, but another node. So it's basically a reference. So when you upload, we know where to send the information to.
Thanks for the answer. That's an amazing feature. Cool. Okay, I think that's all for now. So
I have one question for you, everyone, and I want your answers afterwards. Come and talk to me about this. Did this work? Did you follow along when I was doing the coding and stuff? Did you follow what was going on? I'd like feedback on that, please, because it's like the first time I can do this kind of live coding. So I'd really appreciate it if I got some like feedback afterwards.
Yeah, absolutely. We will take a short break. So if you have feedback for Hans, you can do it right away because we need to switch all of the mics and everything. So maybe that's going to be a good moment. If not, then at the end of the event would be good. Okay, let's hear it again for Hans.